Hi, the lecture today is about what the derivatives of a function tell us about the shape of that graph. So here let's write the title. Okay, that became a long title, but that's going to dictate the tone for this lecture. We said functions are used to study the relationship between variables. If one variable reaches a maximum point and then descends, then locally it's going to look like something like this. Question is, if we have the graph of a if you have the formula for the function, can we tell that such a thing is going on? What's the signature we can use to tell that the function came up and then went down in the vicinity of this point? Similarly, if you have a function that reaches a minimum point, what tools do we have to detect such a thing has happened? Again, the question is just from the point of algebra and calculus. Without having direct access to the graph itself, can we tell such a dip occurred in the graph of a function? Can we tell that the function is going up? Here, suppose I draw a graph of a function. Here, this function exhibiting the behavior that it is increasing. So here we have the issue of a relative maximum. Here we have the issue of detecting relative minimum. Here we have the issue of detecting that the function is increasing. What do we mean by increasing? It means as x increases, so does the y. They go in tandem. Similarly, we have the question of detecting whether a function is decreasing. Decreasing function means as x increases, y decreases. So the question is, can we tell this type of a behavior that the function is decreasing? We have more advanced questions to consider. There are different styles of increasing. Let me draw it on a picture and let me see if you can phrase the definition for yourself. Come up with the discovery of the method also by yourself. A function could be decreasing like this, it could be increasing like this, or it could be increasing like this. You can visually tell the difference between the two of them. But how can calculus, by just using algebra, tell us that a function behaving like this as opposed to behaving in that style? Notice in both cases the function is increasing. We are going up. Suppose you are holding stocks in a company and this was showing the price of a stock as a function of time. This is price and here's time. Which one of these things do you prefer to have your investment in it? Which one? Well, obviously this is the better one. This shows kind of a positive acceleration. It's picking up momentum and increasing even faster. This is kind of dampening out and shows negative acceleration, like it's arresting itself. The terminology that we are going to use for these two cases is called concave up. In this one we call it concave down. This looks like a piece of cup in a normal position, and this looks like a piece of a cup that has been turned down. Same thing could happen for a function that was decreasing. Let's go draw some pictures related to that. You could have a function that is decreasing in this style, or the function could be decreasing in this style. So this one is called concave up, and this one is called concave down. Okay, so this is like the other half of that. If you wish, these two can be joined together, perhaps will be part of the same picture. Once again, what we are going to use, just the derivative of a function, first derivatives and second derivative, to tell us which one of these things are happening. For detecting these cases, we are going to use the first derivative, as we are going to see shortly. For detecting which one of these cases is happening, we are going to use the second derivative. Excuse me, for detecting if the function is concave up or down, we are going to use the second derivative. Now let's go ahead and explain further. So first of all, what does it mean for a function to be increasing? Suppose a function is defined on a certain interval and it is behaving in an increasing fashion. What does that mean? Well, it means that if you have certain value of x and then certain larger value of x, then the value of the function at the second point is more than the value of the function at the first point, regardless of the choices for these two that you have made, so long as the second point is larger than the first point. So if x2 larger than x1 implies that f of x2, let's write it this way, f of x1 is less than f of x2, we call the function increasing. Similarly, if I had a graph where again I have x1 and here is x2, the x2 is larger than x1, but I'm descending, so at larger values of x I'm recovering smaller values for the function. So if f of the first point is larger than f of the second point, we say f is decreasing. So that one prompts with the following definition, that f is increasing, and this one gives us that f is going to be labeled as decreasing. Now there are slight variations with respect to these definitions by allowing perhaps equality and such, but we are not going to be splitting here on those issues. Let's move on. Well, how can we tell f is increasing? In general, it's not a easy task if the function f is just an arbitrary function. But if f is a differentiable function, if it has a derivative, then we can use the mean value theorem and easily prove the following, that a function that is increasing and has a derivative, then it's going to have a positive derivative. Okay, so if it is differentiable, the derivative has to be positive. Why so? Because if it is going up, its tangent line is pointing upward, tangent line pointing upward, then slope of tangent line is going to be positive. Slope is same as the derivative. That's going to tell us that the derivative is positive. So this case is assuming the function is differentiable, same as saying that the derivative of the function inside of that interval is positive. Okay, so that's going to be our main tool. You want to check to see if the function is increasing, check its derivative. If it turns out to be positive, then it is increasing. Same story here. If a function is decreasing and it is differentiable, meaning it has these tangent lines with defined slopes, then the slope of these tangent lines is going to be negative. So the signature of a decreasing function is that its derivative is negative. So any question with respect to finding out the domain of increase or decrease is answered by analyzing the derivative of the function and figuring out where it is positive and where it is negative. In addition to this, if we have a function that is exhibiting a behavior like this, if it has an increasing interval followed by a decreasing interval, then we can easily say that there is a maximum point, a relative maximum, just at the point that the two behaviors are separated. So here we have interval of increase, we are going up. Here we have an interval of a decrease. In between we are going to have a relative maximum. So if we can detect first a positive derivative, then a negative derivative, then in between we have a relative maximum. At what point would this thing happen? Well, if the function is differentiable here, the derivative will be 0, and the other alternative is that the function isn't differentiable there. Like for example, let me draw. It could be that the function was increasing, came to abrupt sharp point, and started to decrease. At this point, the derivative would not exist here. Still, we have an increasing behavior first, a decreasing behavior afterward, and we have a relative maximum in between. Most often you encounter these type of situations, but every now and then you might see a function that behaves like this, rather unusual behavior, but it could happen. So what is going to be a general name for both this behavior and that behavior? At this point, tangent line exists, the derivative exists, the derivative is actually 0. At this point, the derivative doesn't exist. So these two fall on the category of a critical point. So if we have a point, if we have a critical point, we go ahead and do the following. We have the first derivative test. The first derivative test is going to give us a procedure for finding and labeling maximum and minimum points of, excuse me, so this is essentially to find relative max and relative min, as well as intervals of increase or decrease. So we are going to harvest a lot of information based on this test. And the way we proceed is the following. First, find critical points. Again, what are the critical points? Critical points, let's call it critical point C. That critical point C is referring to such points. Critical points have the property either the derivative at that point is 0 or the derivative at that point does not exist. So we have a function that is defined on an interval and it is continuous all the way through. There is a point at which either the derivative is 0 or perhaps the derivative doesn't exist. Let's consider call this point C. Say in step 2, if f prime is positive before C and negative afterward, like that. The derivative was positive if we are going up and the derivative is negative afterward. Then at that point we have a maximum. Same thing here. The derivative was positive, then it became negative. In between, the derivative wasn't even defined, but that doesn't matter. You still have a relative maximum. What's the other possibility? Let me draw the picture of the other possibility. Suppose you have a function, you find a critical point, say critical point here, and you discover that before the critical point the graph is exhibiting a descending behavior. It has a negative derivative, and after that it has a positive derivative. So really you have an interval here which shows f is decreasing up to here, f is increasing afterward, and at that point it realizes it's on relative minimum. This graph suggests that the derivative at this point exists and is actually 0. It could be that the derivative changed its behavior by a slightly different kind of process. That is, the function was decreasing and then at this point started to increase, but at the point itself the derivative doesn't exist. We still have a decreasing behavior on the left, increasing behavior on the right, and at that point we have still a relative minimum. So if we go ahead and say if f prime is negative before C, that is, here as we come down f prime is negative, slopes are negative, and f prime is positive afterward, and f prime is positive after C, then f has a relative minimum at C. Now, is there any alternative left? you go ahead first find the critical points. At critical points the derivative either is 0 or doesn't exist. Normally one of these two cases will happen, but sometimes neither of them might happen. Here is the alternate picture. So I could have a function that reaches a point at which the derivative is 0. So we have gone ahead and found a point C at which the derivative is 0. The derivative being 0 means tangent line is going to be horizontal. If tangent line is horizontal, are we guaranteed that we are going to turn around either way? Well, not necessarily. The graph might behave like this. It could be that it is increasing up to this point, and even after that it is still increasing. So it is increasing here, it is increasing here, and when that happens we just designate that it is increasing everywhere. Even though the derivative here is 0, that doesn't bother us all that much. We say the function is increasing everywhere. It could have been that you discovered a critical point at which the derivative is 0, meaning tangent line is horizontal. It could have been that the function was decreasing up to this point, and after that still kept decreasing. So it could be decreasing followed by decreasing behavior. We just call the whole thing, the function over the whole interval is decreasing. We are not going to designate this as a maximum or minimum. Some other names for it, but it's not maximum or minimum. The other alternative for this picture is the following. Remember, our first objective is to go find the critical point. So suppose I find the critical point here, and the function is not differentiable there at all. For example, it could behave like this. I could be going up to this point, so that at this point the derivative is infinity, and then I might continue building and going like this. So tangent line, if you wish, exists. It's just a vertical tangent line with undefined slope, but tangent line itself exists. Well, here we are going to go ahead and say the function is increasing here. It was increasing there. Over the whole interval, still increasing. We don't need to designate separate intervals for intervals of increase. And as you might guess, the other flip side of the coin could occur also. You could have a function that decreases in this particular way. Perhaps as a point at which the derivative doesn't exist because it is infinity, and you have designation of decreasing here, it's decreasing here, and over the whole interval you just describe it to be decreasing. So here we are going to put a subcase, or maybe I just write it separately. If f prime does not change its sign at C, then C is neither a max nor a min, but we can tell that the shape is one of the followings. There are other possibilities also. I just drew some of the most typical cases. for problems you might encounter. There are still other possibilities. For example, the fact that derivative does not exist doesn't necessarily mean it is infinity. Perhaps it is behaving like this. You are increasing up to some point, say, and at that point the derivative doesn't exist, but you keep increasing at a different slope. That's the same designation. You have an increasing behavior followed by another increasing behavior. That point, even though the derivative doesn't exist and it's designated as a critical point, there isn't much of anything special occurring at that location. Same way here, it could be a function is decreasing, encounters a critical point, then it keeps decreasing afterward. Okay, all of these are rather special cases. You see some of these every now and then. More rarely you might see some of these, and it's quite uncommon to see some of this at this level. Later on, maybe in your advanced classes you deal with this kind of functions, but not right now. The important thing to remember perhaps are these pictures. This picture, something you need to remember, this one, and perhaps these. Okay, let's go ahead and do some examples. Suppose I pick a problem here. Suppose f of x is an example. F of x is given to be equal to, say, 2 plus 3x minus x cubed. Rather simple function, is a cubic function. Question: find intervals of increase and decrease. Find relative max or min, and use this information to graph the function. Okay, how do we proceed? All of these things are answered by applying the first derivative test. That is, we need to go first derivative test, find the critical points, and try to figure out if it is positive or negative, which means we have to solve an inequality. So the inequality problems you learn in college algebra are going to come in handy here for solving this. We are going to quickly review that procedure as well. So what do? I go ahead, find the derivative. Derivative of 2 is 0, derivative 3x is 3, and the other one is minus 3x squared. I have to find critical points. Once again, what are the critical points? Are the derivative is 0 or derivative does not exist. Luckily, this category is out. Derivative always exists. There is no problem here. We never encounter with not being able to calculate the derivative. So this category doesn't show up in this problem. F prime equal to 0, well, that can easily happen. Let's go ahead and solve this. 3 minus 3x squared equal to 0. You might factor 3 or divide by 3. You find out 3 is equal to, let me go ahead and solve this here. I divide by 3, x squared becomes 1, so x becomes plus or minus square root of 1, which is just 1. I found 2 points. These are my critical points. So I say critical point x is equal to plus 1, x is equal to minus 1. At both of these, the derivative became 0. I remember where they came from this category or this category. Next, to put everything in a nice format, we are going to have something, we call it a sign chart. So here is our sign chart. Sign chart is going to help us figure out all those inequalities. We go ahead, make a x-axis for ourselves. Here I say x-axis. Whatever the domain of the problem, I write it. Well, these problems typically go from minus infinity to plus infinity, so that's just my entire x-axis. All the critical points I found so far, I lined them up in order. I have minus 1 and then I have plus 1. Here I write my derivative f prime, which is 3 minus 3x squared. What do I need to know about this derivative? I need to know, is it positive or negative? Remember, the whole issue in this section was everything depends on the sign of the derivative. You need to know that to make your verdict. So here we go ahead, try to find the sign. Finding the sign is same as solving an inequality. What's a quick way of solving an inequality? You go ahead, find test points. So find a point here, say what's a good point, go by the whole small numbers, say minus 2. Take minus 2 and plug it in this f prime. Let's do it here. 3 minus 3 times minus 2 squared. What is that? 3 minus 3 times 4, that is 3 minus 12, that's minus 9. You have to make sure that you do this calculation correctly. Essential thing is that if you go wrong and this sign is incorrect, then your entire verdict is going to be off. So you double check yourself several times here. The important thing is that we found out that when we put a minus 2 in this, we get a negative number. There's a little theorem that says if you choose any other test point from here to here, you're going to get the same answer. That's a nice thing about it. So we know for all the numbers from minus infinity to minus 1, the derivative is negative. Now I go ahead, pick another test point. Between minus 1 and plus 1, easiest test point is 0. If I plug it here, I get plus 3. So here's another test point, 2. If I take 2 and plug it here, just like in this case, I'm going to get negative number. What if I plug minus 1 and plus 1 here? Well, we know what we are supposed to get because these were the roots. If I plug minus 1 in this, I'm going to get 0. If I get plus 1, I get 0. Now I go ahead and draw some lines here. Right underneath the critical points. My verdict is going to be written on this line. I'm going to say the function f. I want to know how does the function f behave. So if the derivative is negative derivative, you remember what does it imply? It implies the function f is decreasing. Positive derivative means it is increasing. Negative again means it's decreasing. Sometimes it's good to show this by some arrows. Decreasing means the function is going down. Not necessarily in such a straight fashion, but that's just the simplest statement we can make. It's decreasing, going down. If it is increasing, you show it by arrow like this. Decreasing again, you show it by arrow like this. So far we have the following answer to our question. First question was find intervals of increase and decrease. Let's go ahead and designate this. So this is the interval of decrease, this is another interval of decrease. So I write that here, intervals of decrease are two intervals, from minus infinity to minus 1, and the other interval is from 1 to infinity. Interval of increase, there is one such interval, it just goes from minus 1 to 1. We were asked to find relative maximum and minimum. The answer is rather obvious. If you are coming down and then you are going up, in between you are going to have what? Coming down and then you are going up. So this point is going to be designated as write it by different color. This is going to be a relative minimum. Again, we came down and went up, so it had to be relative minimum. We went up and then we came down, so this point had to be a relative maximum. So we say a relative mean at, sometimes the x value is enough, sometimes we are asked for more than that. Remember our function, maybe we write the function itself here so we don't forget. F was 2 plus 3x minus x cubed. So 2 plus 3x minus x cubed. So if x is minus 1, to find the y, we have to go here. So 2 plus 3 times minus 1 minus 1 cube. That's going to be 2 minus 3 plus 1. Apparently we got 0. Relative maximum at x of it we found here. X of it is plus 1. Y of it, well, let's go through this thing again. 2 plus 3 times 1 minus 1 cube is 2 plus 3 minus 1, and that makes it 4. So with the information that is given, what is the graph that we can draw? We go draw our x and y coordinates. We choose our units so that the picture is not too small and important points are still on the page. So I have minus 1 and 0 to show that, say minus 1 and 0 is here. What was the significance of it? Significance of minus 1 and 0 was that that has to be relative minimum. The other point was 1 and 4. Let me designate, use a different color here. One and 4 perhaps goes at that point. So our function, the way we discovered it, from minus infinity to minus 1, it's supposed to be descending. Then from here to the maximum, it's going up, and then it's descending again. We try to draw a smooth curve having such a property. So from infinity, we are coming down to 0. Pull up. and then we are supposed to descend again. So this becomes the graph of the function y is equal to 2 plus 3x minus x cubed. Okay, now you want to go ahead and practice a few more of these graphing problems. We go ahead to the next topic, which is the second derivative. What's the role of the second derivative? The role shows itself even in this picture I just drew. Here I'm decreasing, and I'm decreasing here as well, but the way I drew the function was quite different. Since I anticipate other question coming up, I already knew how to draw this thing, but the first time that you encounter this, you have to work a bit harder than I am. Notice here the function is concave up. Over here the function is concave down. Can algebra help us to figure that out before I start drawing the graph itself? And the answer is yes. So we are going to go ahead and talk about concavity, perhaps a little bit harder for you than the issue of the first derivative. Let's go ahead and make some room. And so I'm going to talk about concavity. This issue can be handled in a variety of ways. I'll explain 3-4 different ways of looking at concavity, and then we just come down to the favorite method we have in calculus for detecting the style of concavity. Suppose you have a curve looking like this. You want to know what are the distinguishing characteristics that separate that one from this one. Visually we can say this is opening up, this is opening down, but that's begging the question. If the graph wasn't drawn and all you were given was a formula, how can you tell which one of these two will be the case? So we are looking for some clues in that regard. Clue number one is that if you draw a chord, that is, if you connect 2 points of this graph, can you tell what is the difference between the chord here and the chord there? Well, it is obvious. In this case, which we call it concave up, in this one we call it concave down, each chord is above the graph. Here each chord is below the graph. That's one way to tell. But again, you have to have the graph and chord drawn to know that. If the graph isn't there, this is not going to help us. But it helps us to understand what the concavity is. Here's a clue number 2. If I have tangent line here and a tangent line here, quite obvious again what the difference is. Here, tangent line is below the graph. Here, tangent line is above the graph. Once again, it's not going to help us to figure out which one of them is happening unless the picture is already drawn. And if the picture is already drawn, the puzzle is already solved, there isn't really much to do. So we are still looking for something else. let me go ahead and draw several tangent lines. Here, tangent line, here's another tangent line drawn at the point further on. So this was tangent line number 1 at the beginning, tangent line number 2 drawn at the higher x. Here's tangent line number 1, here's a tangent line number 2 drawn some other point later on. Can you see what's the difference between these two? Maybe you want to pause for a moment and detect the difference between the two pictures. Did you figure it out? Well, again, as you see here, as you go from the left to right, your tangent line is rotating in a clockwise fashion, counterclockwise fashion. As we go from left to right in a graph that is drawn in a normal fashion, as we go left to right, the tangent line turns this way, as opposed to picture that is concave down. As we go from left to right, tangent line is rotating in a clockwise fashion. So let's write that down. Tangent line rotates in counterclockwise fashion or direction as we go from low x to high x. Let's just simplify to say as we go from left to right, a normally drawn picture. Here, tangent line rotates in clockwise fashion. As we go from left to right. Again, this is our third attempt at discovering something that is still not helpful. You still need the whole picture to figure out where it is turning. But this last statement is going to give us the clue, the final clue to get the algebra right. From the first tangent line to the second tangent line, here you notice as you turn this way that the slope of the tangent line is increasing. Is that right? Slope of line 2 is higher than the slope of line 1. So that means slope itself is an increasing function. If a function is increasing, its derivative is positive. So here's our next clue. The derivative of slope is positive. Let me repeat again. As we go from 1 to 2, slope increased. A function that is increasing has a positive slope that we had at the beginning of this lecture. Let's go all the way back. If a function is increasing, any function, if it is increasing, its derivative is positive. Now what we are saying is that the slope is increasing. Slope is increasing. Let me write it here perhaps to help you. Slope is increasing as we go from left to right. In this case, slope is decreasing as we go from left to right. Well, if something is increasing, its derivative is positive. Now let's go make it a mathematical notation. slope itself was the derivative of the function to get. So here is the slope. Slope is a derivative function. Now we are talking about the derivative of that. So it's a derivative of the derivative is positive. Here we have the derivative of the derivative is negative. Finally, here's our holy grail. Second derivative of the function is positive in this case. Second derivative of the function is negative in this case. That is our discovery of the day. Let's emphasize second derivative positive is for graph of a function that is concave up. Any portion of this has a positive second derivative. Any portion of this graph has negative second derivative, and that is a concept you need to digest very well. Let's go ahead and take the same problem we looked at a few moments ago, and I ask you to find intervals of concavity of f of x is equal to 2 plus 3x minus x cubed. What do we do? Well, you know how to find the first derivative. First derivative was 3 minus 3x squared. Second derivative, I take another derivative out of this. All I'm left with is just minus 6x. Remember, again, we need to know the sign of the second derivative. So I go ahead, make a table. So I make a second derivative sign chart. It's going to look something like this. Here's, I make my x-axis. It goes from minus infinity to plus infinity. I want to know when is this thing positive or negative. So I go ahead, find all critical points of it. So I go ahead, set second derivative equal to 0. Find the roots. The root is simply just x equal to 0. If I had more than this, I line them up. If there was a point at which the second derivative was not defined, I also include it here. Here I write the second derivative. Second derivative is minus 6x. Go ahead, choose a test point, such as just say minus 1. Between these two, pick a test point. Pick the test point, plug it here. You see that you get positive 6. At this point, second derivative is positive. Pick any other test point in this range, you still get the same sign. It's always positive. Pick a test point on this side, plus 1. You plug it here, obviously you get minus. What this says is that for any number between 0 and plus infinity, the sign of the second derivative is going to be negative. We are going to separate these two into two cells. What is our verdict? Our verdict here is that the function f itself, since it has a positive second derivative here, it's going to be called concave up. Since it has a second negative second derivative, it's going to be considered concave down. our final answer is gonna be written like this: F is concave up on, this is a range of numbers on which we have this designation. So from minus infinity to 0, it's concave up. It is concave down on from 0 to infinity. From here to here is going to be concave down. If you want to help yourself in graphing concave up, you remember it means it resembles a piece of curve that looks like this, like a cup in normal position, and this is going to look like a piece of a cup in inverted position. Let's go back and see if our graph was showing this. Here's a graph we had drawn from minus infinity to 0. This is supposed to be concave up. Our picture is almost correct. Let me color it from here all the way to 0. All over here was concave up. At this point, flavor of behavior changes. It becomes like a cup in an inverted position. So it goes down like this. So here is concave down. One item left. The point that separates these two behavior, that gets to have a name also. This point is referred to as the inflection point. Inflection point is a point at which the function, its first derivative are defined, the function is flipping from up behavior to down behavior, or perhaps from down behavior to up behavior. We have the same name for either of those two events, as opposed to maximum, minimum, that we have two different names. But here, if you go from up to down, or if you go from down to up, like here, was function concave down, and then it became concave up, this point is also going to be called inflection point. So something we need to remember. The inflection point at x of it is 0. This point at which concavity changed is an inflection point. X is 0. What is y? You plug in the function itself, original function itself. You plug x equal to 0 here, you get y equal to. That is the point on the graph. This point is a point with coordinates 0 and 2, which is the inflection point. Final item for this lecture is an application of the second derivative. It's called the second derivative test for maximum and minimum. This is a rather slick and tricky way of trying to distinguish maximum from minimum without doing the first derivative test. Let me take you back to our original picture and explain to you what the issue is. You remember we started with this problem, and one thing we wanted to find out was the maximum minimum. So the procedure starts always like this: find a critical point, and we go ahead, normally we're dealing with the derivative being 0. We go ahead, find the roots. There could be multiple roots here. Question: is there an easy, quick way of telling which one is the maximum, which one is minimum? Who is who here? We answer that question by doing a sign chart for the first derivative. Can we avoid that, or perhaps can we find a detour for answering the same question? So again, we have found a point at which the derivative is 0. We are trying to figure out, is it maximum or is it a minimum? Let's go ahead and practice this question and see the significance of the answer. Suppose I tell you that this is a point at which the derivative, first derivative, became 0. So I know there is a horizontal tangent line here. How can I tell if it is a top of a curve or a bottom of the curve, or perhaps neither? Suppose I know that second derivative is negative in the vicinity. Let's call this point C. I say second derivative is negative at this point. Okay, second derivative is negative. Well, second derivative negative, you remember what it implies about the shape of our function. What does negative second derivative mean? Negative second derivative means the function is concave down. So if it is concave down, what can this thing be? Can it be a minimum or a maximum? If it is concave down, it is forced to look like this. If it is concave down, so it means f is concave down at C, hence C is a local maximum. See how tricky the reasoning is? If you know the derivative is 0, and you know the second derivative is negative, you automatically conclude that it had to be a local maximum. You don't have to go through the trouble of making the first derivative chart. Similar reasoning applies in the reverse case. Suppose that there is a point C at which the derivative is 0, so we have f prime of C is 0. Second derivative in this case is positive. What we can conclude is that if second derivative is positive, f is concave up. If it is concave up, look, would be a cup in a normal position. So this point had to be the bottom of it. It cannot be top of that picture. So C is a local min. Okay, what is left now to do is just to practice the questions, problems. You need to do perhaps 10 problems from this section to get the hang of it. The concepts are simple and intuitive. The problems are more or less straightforward. You just have to take the first and second derivative correctly and find the critical points, set up your table and double check your answers, and then you'll be all set. Okay, you go ahead and practice those, and we see in the next section some practice problems related to these questions. Good luck and God bless.